back. So next up, we have Pradeep Ravikumar talking about learning Minimax estimators via online learning. Take it away.
Let me unmute myself. So thanks to the organizers for inviting me to speak at this workshop. And thanks to all of you for attending this talk as well. So what I want to talk about today is what one should really call learning to learn. So let's see, of course, learning to learn is kind of an overloaded term. So let's see what I mean by that specifically. So the basic setup is common to just standard statistical machine learning. So I'm given n IID samples, x1 through xn, drawn from some statistical model, p theta star, with parameters theta star, that are really lying in some domain capital theta. Okay, so my overall family of statistical models is given here, and the goal in statistical machine learning is to infer the underlying statistical model p theta star, or just imagine it's theta star if the model is identifiable, from just the samples x1 through xn. So that's the learning problem. Under various assumptions in the family of statistical models and the domain and the type of samples, we have different estimators, different algorithms, different analyses, and so on. So let's now zoom in a little bit into estimators or learning algorithms, if you will. So I'm going to denote that by theta hat. They take as input a set of samples. So here script X is really the domain of an individual sample. So you're given a set of samples, and the goal of the estimator, given the set of samples, is to output a parameter, right? Now, the question then is, so this goes again to the foundations of statistical machine learning. How do I then talk about what a good estimator is? Again, the first few slides are essentially just going to be just setting up the notation of something that is very standard. So how do we then talk about a good estimator? The way we talk about a good estimator is through the lens of a loss function that, in this context, imagine takes as input two potential parameters and tells us how far apart they are. Okay, so essentially, if the true parameter or model is theta star, and I output theta hat of x1 through xn, right? So this is again the output of my estimator. This tells me the loss that I would incur. Now, because the set of samples is random, the estimator or the output essentially of my learning algorithm itself is random, and so would be the loss. So it could be either extremely unlucky or extremely lucky. So it's typically much more natural to talk about the risk instead. And what we mean by risk in machine learning is really the expected loss. So here, what am I taking the expectation over the samples, the n samples that I'm drawing from the underlying statistical model? So here, the two arguments are the true statistical model, theta star, and this is now a learning algorithm or an estimator, okay? So given this notion of risk function, I can then ask, hey, give me a learning algorithm that attains the minimum possible risk. But the problem with this question is that there's a very trivial answer to that, which is that I think of this constant estimator that no matter what samples I see, I'm always going to output theta star. Okay. Now you can see that this would have essentially zero risk for most reasonable loss functions. And that makes it, you know, kind of a very trivial answer to what is a very complex question. So a way to get around this, right? But this is clearly a bad answer if my model was slightly different, right? So if my model wasn't theta star, but maybe theta star prime, right? Then this would give me a very, very wrong answer, right? So how do we talk about that? We really need a global notion of optimality where I allow for multiple possible statistical models that could be true. And so one very natural notion is worst case optimality or minimax optimality, which you can think of as saying that I'm going to allow nature, so no matter what learning algorithm you pick, okay, so this is theta hat, which is my estimator, you're going to allow nature to pick the worst case statistical model, okay? So once I fix theta hat, this gives me the worst case risk that my learning algorithm would satisfy, would incur, and then my goal is to find the learning algorithm that would suffer the least worst case risk. Okay, so this is minimax optimality. And obviously, this is a very, very well-studied notion in statistics and statistical machine learning. But how do we obtain minimax statistical estimators? The typical way it is done is really problem-specific approaches where I think about what are the class of statistical models I'm working with, what is the loss function, what is the domain, right? And all these different facets, and then I hand construct minimax estimators that I would then argue through post hoc means that it is at least approximately going to solve this optimization problem. But in general, we don't even explicitly grapple with this minimax optimality to begin with. We typically have some other estimation principles like likelihood principles. Maybe I have a Bayesian estimator with some reasonable prior, maybe non-informative prior, whatnot. And I come up with the estimated theta hat. And then I want to reason that, hey, it is actually minimax optimal, if not exactly, in the sense that it exactly solves this min-max problem, at least it's asymptotically, meaning the limit as the number of samples n go to infinity, maybe allowing for some constant factors and so on. Okay, and we typically do that using various information theoretic tools. Again, it's an information theory question because we really don't see theta star. We only see a lossy facet of it, which are the n samples. So this is the state of affairs. And the question that we wanted to ask was, is it actually possible to algorithmically derive, in other words, learn how to learn, meaning that learn how to estimate by solving this min-max problem? It is, after all, a min-max, reasonably well-defined min-max problem, right? So why not just solve it, right? So essentially, if I look at this, the min-max problem, one way to look at it is as a zero-sum statistical game between, and this is how, in fact, if you open up any decision theory textbook, this is how it is motivated, as really a statistical game between a learner whose action space is the set of possible estimators. Okay, so if I'm the learner, my action would be to come up with an estimator theta hat. And it's a game between this learner and nature, which you can think of as the adversary, which can pick any statistical model it so desires from the given family of statistical models. Okay, so it's really this min-max game between these two players. And the question then is, can we solve this zero-sum statistical game algorithmically? No matter what the loss function is, no matter what the domain is of either the samples or the parameters. Now, stepping back a little bit and just thinking about this min-max zero-sum game or zero-sum game, if this risk function is actually convex concave, remember that I'm minimizing with respect to the estimators and maximizing with respect to the true model parameters. So I really wanted this function, this bivariate function, to be convex in the first argument and concave in the second argument. And if that is so, something that looks like this. Okay, imagine that the estimator is one-dimensional and the distribution is one-dimensional. It's not, right? But let's just imagine then you want, if you look at this with respect to the distribution, it is concave. Actually, you can see it's concave here, right? It's an inverted bowl. But if you look at it with respect to the estimator, it's convex, right? So if it's something like this, then the min-max is equal to the max-min, right? So this is a very, very classical theorem. And this the resulting optimal solution is called, again, the classical Nash Equilibrium. And there are actually many efficient algorithms to obtain the Nash equilibrium, including just very simple gradient descent ascent. Okay, so I just iteratively update theta hat and iteratively update theta star just along the gradients, respective gradients, and that would converge to the Nash equilibrium, provided R is convex concave. Right? So everything would be wonderful if R is convex concave, but the unfortunate reality is that even for very simple things like squared laws and linear regression and stuff like that, the statistical game is not convex concave. It'll look a lot more like this rather than the very nice figure in the previous slide. So in particular, the min-max theorem is not going to hold. Okay, so min theta hat max theta star is not going to be equal to max theta star min theta hat. That's definitely one thing. But the other more critical problem is that this is a very, very difficult optimization problem to solve, especially considering, even setting aside the non-convexity, considering the domain of theta hat, which is the set of all possible estimators. Okay, it's clearly a very, very large set. So what do people typically do when faced with such non-convex concave games? Okay, let's not worry too much about the domain, really intractably large domain for now. Let's just imagine, in fact, even just a typical finite zero-sum games. If it is if it's finite, it's relatively easy. But for simple zero-sum games, how do I solve such a zero-sum game when R is not convex concave? What we typically do is we lift the problem, so what is done is you linearize the game. So instead of the actions being the set of possible estimators, like here, right, and the set of possible models like here, you have distributions over estimators and distributions over parameters. And then what your objective is essentially which is basically the loss that, for instance, the learner would suffer would essentially be just the expected risk with respect to these distributions. Okay, so this is basically the reason I call it a linearized game, is that this guy is actually linear with respect to these distributions, right? So for instance, imagine this is discrete, right? And its domain is, imagine that there are only k estimators. So then this would just be the k simplex, right? And you can see that this would just be a summation of, it would just be a linear function of those multinomial parameters, right? So that's the linearized game. And now, because this is bilinear, linear in both the actions of the learner and the actions of the of nature, it's bilinear and hence convex concave, right? So the Minimax theorem holds, and there does exist a Nash equilibrium of this linearized game. And so we call the Nash equilibrium of this linearized game as the mixed Nash equilibrium of the original game. Okay, the original game, I just mean this guy. Oh, okay, so far so good, right? So maybe if I can just lift the problem, then I'm in the convex concave space, then maybe I can just do gradient descent ascent and solve this statistical game, but not so fast, right? This is maybe relatively fine, but this guy is a distribution set of all possible distributions over all possible estimators. This is impossibly large. If you think about the typical algorithms to solve games, they are not really designed for such large, complex games. And of course, we are also, many of the results are also break down when, even in this linearized setting, when this R is not convex and the domains are infinite. So what do we do, right? So recently, an approach that has really, it's kind of an old approach, but it's really caught quite a bit of, attracted quite a bit of interest in recent years, is to solve such zero-sum games by a reduction to online learning. Okay, so again, the zero-sum game, think of it as just a one-shot game, right? The learner picks an estimator, nature picks a theta star, and then you suffer a loss, right? It's just a one-shot game. But let's drag this out to over multiple rounds. And the learner then, in each round, so this is, of course, a general online learning setup. So let's actually talk about the general online learning setup in case it's not familiar. So again, this is general online learning, where a learner will pick an action. So again, I'm realizing a little bit of an unfortunate notation, but let's stick with it. The learner picks an action, and the adversary chooses the loss function itself. Okay, and the learner would then suffer the loss function applied to the specific action that the learner chose. Okay, and this keeps happening over multiple rounds. And the overall loss the learner suffers over t rounds is basically just the sum of the losses they suffer in each round, right? But because the adversary gets to play after the learner, they can always choose an FT that is maximally harmful to theta t, right? So this becomes like a trivial problem. So to make this interesting, the goal is to actually minimize the regret with respect to a single action that is chosen in hindsight. Okay, so here, these are all the losses that I would suffer in t rounds, and then my goal is to pick the best action in hindsight. And the regret is the overall loss you would suffer compared to this the loss of the best action picked in hindsight. And the goal in online learning is to really do well with respect to this, so that the overall regret is sublinear in t, which means that the average regret per round is small o of 1. Right? So you suffer less than constant regret per round. Right? So that's what you want, vanishingly small regret as t goes to infinity. Now, this is, again, it's a very, very important framework, and there's been a lot of work on algorithms to achieve regret that is sublinear in t, even when these loss functions are not convex. Okay, there was in fact a recent work that won the best student paper award that showed that even when these functions are non-convex, there exists simple algorithms like follow the perturb leader, which you can think of as something like regularized ERM, if you will. I'll come to that. But the very simple algorithms achieve sublinear regret. Okay, so that's basically just a quick detour into just generic online learning. So why is this helpful to solve a statistical game? So again, the statistical game is just a single shot zero-sum game, right? Learner picks theta hat, nature picks theta star, you suffer a loss. So one way that I can actually figure out what is the Nash equilibrium, if you will, or mixed Nash equilibrium, is to have the learner and nature play multiple rounds. Okay, so over t rounds, the learner picks estimators theta hat t, okay, and or let's call it theta hat s, and but actually we're going to play the linearized game, so the learner is going to pick a distribution over estimators. Okay, so let's call that p theta hat s in the s round, and the nature is going to pick a distribution over possible parameters. Okay, let's call this the distribution it picks in the s round, and each player would be trying to so it's like online learning, right? So each player would try to minimize their regret with respect to the other player's actions. So imagine that both of them play sublinear regret algorithms, or let's imagine that the specific regret of their specific algorithms is epsilon L for the learner and epsilon N for nature. Okay, so both of them are essentially playing the sequential game, and imagine that this is the regret each of these guys are going to suffer after t rounds. Now, let me construct this randomized estimator that's basically just this mixture model over these distributions. So each round itself, I'm playing a randomized estimator, and I'm essentially going to take a uniform distribution over mixture over all of these various distributions. So this is in turn a randomized estimator, or if you want to think about it, it's a distribution over all possible estimators. And let's construct with respect to nature, again, this mixture model, which is again just a uniform mixture or all the actions that nature took over the t rounds. Then what you can show, again, this is just a few lines of proof that it's a very simple statement that essentially this theta hat, this randomized estimator and this mixture are actually an approximate mixed Nash equilibrium of the statistical game. Okay, and the approximation factor is precisely the sum of the regrets. Okay, so in other words, if I have a vanishingly small regret, if the learner and nature play online learning strategies that have vanishingly small regret, they essentially get a very, very good mixed Nash equilibrium of the original game. Right? Now, so far, so good. But if you, again, think about all these online learning algorithms, how is learner going to actually use all of those approaches, online learning approaches, when most of either the analysis, in fact, the algorithms themselves, the computational complexity really scales with the size of the domain. And even the statistical complexity typically scales with the size of the domain. And so this is infeasible when the learner's domain is exceedingly large, right? You're looking at distributions over all possible estimators. So how do we then choose sublinear regret strategies for learner and nature that are simple? It seems impossible, right? But it turns out that there is a very, very simple sublinear regret strategy that is in some sense cheating. Okay, you just make the learner act after nature has chosen its action for that round. Remember that here you are still free to decide any sublinear regret algorithms, and this theorem holds, right? And so what I'm saying here is that the estimator is actually going to pick the best possible estimator for that round T after nature has picked a distribution over statistical models at that round T. Okay, so this is called best response. This is typically not going to be available in general online learning setups, right? But I can do this, right? This is definitely a sublinear regret strategy, right? You would suffer a regret of 0. Actually, you will suffer negative regret because you are optimizing your strategy for the Tth round exactly to the strategy that nature played at round T. Now, if I just think about this again in the context of the statistical game, this is actually a reasonably well-defined, well-studied problem. In fact, this is the Bayes estimation problem, where I have a distribution over models given by this P theta star T. And then my goal is to find the theta hat that minimizes the risk. And this is basically, this expression here is the Bayes risk with respect to this prior. So all I need to do then is to compute the Bayes estimator theta hat with respect to theta hat T with respect to this distribution. Now, don't get me wrong, this is a computationally difficult problem, but this is a very, very well-studied problem in statistics and machine learning, where given various priors, we have various strategies to compute the Bayes estimator. Okay, so this is basically a well-defined strategy, right? Now, what about nature? Nature, what it plays is follow the perturb leader. Now, follow the perturb leader in the context of nature is a little bit more tractable because nature is still working with a finite dimensional space, right? Again, I'm going to assume that the set of model parameters are finite dimensional. And of course, I'm dealing with distributions over this finite dimensional space. So follow the perturb leader actually outputs a distribution. So what it does is that you have some noise variables that are chosen from some distribution. So in our context, we use the exponential noise with some noise parameter eta. Now, once you pick this noise, then what you do is that you just sum up the losses or risks, I should say, that any candidate theta would suffer given all of the estimators that the learner picked in the first T-1 rounds. Okay, so this is the nature's action in the Tth round. Okay, so in the Tth round, nature looks at all the actions that the learner has picked in the first T-1 rounds, right? And it looks at the total loss, total risk, I'm sorry, that any candidate theta would suffer. But then you also add this noise term. Oops. Also add this noise term, and then nature would try to optimize for theta that maximizes this. So this is follow the perturb leader, because if I didn't have this noise term, this optimization with just the first term is called follow the leader. The leader, because I'm just looking at the theta that would minimize, or in this case, maximize the risk the learner would suffer summed up over the first T minus 1 noise. Okay, so this is a very simple optimization problem, right? This is just a finite dimensional optimization problem, maximization problem with respect to theta, right? If I fix sigma, again, sigma is just some noise variables. And by varying sigma, I essentially get a distribution. Because sigma is random, this in turn is random, so I actually get a distribution over parameters. But once I fix sigma, this is a finite dimensional maximization problem. Now, again, this is computationally difficult in general, but in modern ML, we are not faced with non-convex optimization, right? It's par for the course. Again, there are various strategies to try to solve non-convex optimization problems. This is, again, a nice, well-defined problem. So what we're seeing is that both for the learner, which is just base estimator, and nature, which is just a finite dimensional maximization problem, we have well-defined strategies that they can play. And once each of them are playing these well-defined strategies, just computing the average of their strategies in the T rounds, you're going to get an approximate mixed Nash equilibrium, which is pretty exciting, right? So just to formalize basically the computational problems that we need to solve, we cast it in terms of access to oracles. Okay, so I assume that I have access to a Bayes estimation oracle, which again, Bayes estimation tries to solve this problem. Okay, where given a distribution P and the Bayes risk, it tries to minimize, its goal is to minimize the Bayes risk. And my what I'm going to assume is that I have access to an approximate Bayes estimator oracle that solves it up to an additive approximation alpha. And similarly, I'm going to assume that I have access to a maximization oracle. Again, this is a finite dimensional maximization problem. And what is the maximization problem? It's precisely the maximization problem that arises in FTPL, right? Again, you think of this as some typically non-convex optimization problem in theta, and I want to at least solve this up to some additive error beta. Now, given these two things, then I can actually, what we really want is then for the specific statistical game, to say that playing these two specific strategies of TPL and best response, that I get an approximate mixed Nash equilibrium for the statistical game. But I need to make some regularity assumptions. Again, these are very, very standard regularity assumptions to prevent pathologies. So I'm essentially going to assume that my parameter domain is compact. Essentially, its L infinity diameter is bounded, let's say. It could scale with n and so on, and our results actually depend on this d, but it's easier to just think of this as bounded. And of course, the risk function is Lipschitz in my model parameters, so that's also pretty standard. And I'm essentially going to choose the noise parameter in FTPL. Remember that in follow the perturb leader, I'm picking the, I'm adding in perturbing the follow the leader objective with that linear noise with the exponential noise, and these are the parameters, essentially 1 over root t. So d is the dimensionality of the problem, and L is the Lipschitz constant, and P is the number of rounds. Then we have this theorem. Again, it's a natural theorem given the earlier proposition, but with a little bit of subtleties that the regularity assumptions take care of. If the learner plays best response in each of T rounds, the learner plays best response to nature's follow the perturb leader strategy, and given access to the earlier oracles, and assuming the earlier regularity assumptions hold, then the randomized estimator and the mixture distribution for nature, this tuple is actually an epsilon approximate mixed Nash equilibrium of the statistical game. Where what is the approximation factor? It's definitely alpha plus beta of the oracles, but also it scales as 1 over root t. Okay, so this term decays with t, right, as 1 over root t. So the more rounds you play, this essentially is going to decay to 0, so that the overall error that you're going to deal with is basically alpha plus beta, the error of the oracles. Okay, so let's take a step back and see the very, very interesting consequence, right? By playing these rounds, right, I'm learning something about the game. And what am I learning? I'm actually learning a learning algorithm itself, because this guy is actually a learning algorithm. Okay, I want to emphasize that. This guy, given a data set, will output a parameter, right? So I'm actually learning a learning algorithm. Okay, this is basically a distribution over very difficult problems. All right, so this is basically, remember, this is an approximate Nash equilibrium. So this is nature's strategy to force this randomized estimator to suffer the worst loss. So sometimes it's called the least favorable prior. Okay, so that's basically our result, and I'll talk about the consequences of all of this. But just to, to talk about one caveat to this is that I'm providing a randomized estimator. It's not a deterministic estimator, right? So if I'm thinking about, I don't know, solving linear regression using ordinary least squares or ridge regression, these are deterministic estimators. Almost any estimator that we usually work with, though not always, right, are typically deterministic estimators, right? Whereas what this theorem provides is a randomized estimator, right? So what if I want a deterministic estimator? So again, this is pretty standard thing that you do in online learning context, where if this risk is convex in the first argument, not necessarily concave in theta star, but at least if it's convex in the first argument, then all you need to do is just take the mean with respect to essentially this distribution over estimators, and that is just a single estimator, right, deterministic estimator, and that would again have the same guarantees as the randomized estimator. So in that case, what you can show is that you actually have actually have a minimax estimator. So you have a Nash equilibrium rather than a mixed Nash equilibrium. And you can then say, okay, that sounds great, but in general, this risk is not going to be convex in theta hat. What if it is non-convex in theta hat? Which even for simple things like squared losses, it's not going to be convex in theta hat. Unfortunately, even given access to the randomized estimator, coming up with the deterministic estimator is going to be NP hard. Yeah, again, this follows from various standard results. So that's one aspect of this, which is that for general setups, I'm not going to give you a Nash equilibrium. I'm only going to give you a mixed Nash equilibrium, or stated another way, I'm not going to give you a deterministic minimax estimator. I'm going to give you a randomized minimax estimator. Okay, so that's one thing. So which you can think of as a negative thing, or maybe those of you working in randomized algorithms, is like, that's not a big deal. But here is a plus, big plus, I would say. So if the true minimax risk is this, right? This is the, let's say, the value of the statistical gain. Then what our algorithm outputs, remember, is basically an approximate mixed Nash equilibrium, which the way we stated it is basically just an additive approximation factor. So one way to think about this is that I essentially get a randomized minimax estimator whose worst case risk is 1 plus small o of 1 R star. Okay, or to think of it as R star plus something that decays to 0, right? This is in contrast to most analyses of minimax estimators, which are sometimes even called rate optimal estimators, where the worst case risk is typically some constant times R star. Okay, now this constant doesn't depend on n and other problem specific parameters, right? Important problem size parameters, but it could be a big constant, right? And you can see that this is a much more preferable state of affairs compared to this. But that's basically something I wanted to emphasize. Now, that said, right, it's not all good news, because ultimately, we still need to solve these oracle problems, right? Essentially what we have done is reduce minimax estimation to solving two well-defined problems, Bayes estimation and finite dimensional maximization. But in general, these are hard, right? So the question then we were asking was that, could we impose some additional structure on the problem so that these oracles become relatively easy? So one very natural notion that's standard is invariance with respect to group transformations. So again, this is standard. So if I basically have the model parameter theta, then I definitely want for any group element G, when acted on theta, that should also lie in script theta. And again, X is drawn from P theta, then Gx is drawn from P of G theta. And then finally, the loss applied to two transformed inputs is basically the same as the original loss. Okay, so if all these hold, then I would say that the statistical game is invariant with respect to the set of group transformations G. And then I can also talk about invariance of the learning algorithm or estimator theta hat to group transformations if this holds, right? Where I transform each and every one of my samples and then apply the learning algorithm. It's as if I applied the learning algorithm on the untransformed samples and then transform the model parameter. Okay. Then this is standard. In such case, I would say that theta hat is invariant. So what we can show then is that you can take this original statistical gain and reduce it to a reduced gain where I can just restrict myself instead of all possible estimators to estimators that are invariant. And instead of all possible parameters, I can restrict myself to the quotient space, okay, which you can think of as equivalence classes with respect to the group transformation, okay? Which could be much, much smaller. And you can go from one to the other very, very easily. Okay, so again, that's pretty standard. So let's look at the consequence of this for various problems. Okay, so the first problem I'm going to look at is a very, very simple problem where I have a Gaussian distribution and theta star I just identity covariance. And I'm going to give you a single sample X drawn from this Gaussian distribution. And this true theta star is going to be bounded. Okay, so let's say its L2 norm is bounded by B. So given this, this is my statistical gain, right? Minimize over all possible estimators and maximize over all possible model parameters subject to them being bounded, basically the L2 or squared loss between theta hat and theta star. Okay, so this is seems very simple, but again, it is a very, very fundamental problem for consequences, even for general non-parametric regression. You can actually reduce a whole bunch of statistical problems to this finite Gaussian sequence model. So because of that reason, it's a very, very well-studied problem. Okay, but it's also very amenable for us to reason about. But the thing is, exact minimax estimators are actually not known if this bound is large enough. So in particular, if this bound is larger than 1.16 square root D, then nobody knows until our work what is the optimal minimax estimator. Okay, so again, the MLE is just X, right? The MLE of this problem is just X, but that is not clearly non-minimax optimal. There are various estimators like Jane-Stein estimator and so on that essentially shrink the MLE towards the origin that have better performance. But the question is, what is the minimax optimal estimator? And this was unknown. Now, it turns out that this is actually has invariance with respect to the group of orthonormal matrices. And the group action is just matrix multiplication. Now with this, if I look at the quotient space, it's basically, it takes this d-dimensional essentially scaled unit ball and takes the quotient space, brings it down to just one-dimensional interval from 0 to B. Okay, so all I need to work with is this one-dimensional parameter B. and then solve this reduced statistical game. So this is a much more reasonable problem, but I might still need to solve for the Bayes estimator, right? Which could be hard. So the one-dimensional optimization, I can just grid it and just solve it easily, right? The maximization oracle is kind of trivial now. Whatever error I want, right? If I want the beta error, just grid it up to 1 over beta, and then I would be done. Especially under the regularity assumption of Lipschitzness and so on. But what about the Bayes estimation oracle? The thing is, you can derive the Bayes estimation oracle in this context in closed form. Again, I won't go in over the exact expression, but it's actually available to you in closed form. Okay, so in this case, both the oracles have very, very efficient implementations. So I can actually algorithmically compute the Minimax estimator. And that's basically what we did. We looked at various dimensions. We varied the bound to go even beyond 1.16, where again, the Minimax estimator is just not known. And the last two are really our estimators. So, so far I've just talked about the average estimator. So that's the second last line. And in bold is basically just the risk that our estimator suffers, and the numbers in brackets, the duality gap, but let's not worry about that for interest of time. So what you can see is that we do much, much better than definitely the MLE, better than James Stein estimator. You can think of projecting the MLE onto the scaled unit ball. That performs much worse than James Stein, as is well known. But what we are getting is something that's much, much better than any of the classical estimators. Okay, and again, I want to emphasize that Minimax estimators are just unknown in this regime, and we algorithmically derive, right, approximate Minimax estimators. And just to give you a sense that for the case where D equal to 1, Donahoe a few decades ago had derived the Minimax estimator, and he obtained these lower bounds. And what you can see, actually he derived lower bounds, I'm sorry, not the Minimax estimator. And what you see is that the worst case risk is very, very close to the lower bound. Again, the lower bound is not exactly the Minimax risk, right? It's a lower bound, and you can see that we are very, very close to that lower bound. And I want to emphasize that we are provably Minimax, approximately Minimax, right? So that was the finite Gaussian sequence model. Again, it has implications for non-parametric regression and so on. But let's just look at another simple problem, which is a little bit more non-trivial, which is linear regression. So this is, again, just the standard setup where I have, let's say, with random design. So my features are just N0i, standard normal. And yi, the response, is a linear function of the features. And theta star is a model parameter. And these noise variables are also N01. And I'm going to assume that the model parameters are, again, bounded. Okay. So you get this statistical gain. Okay, this is just the squared loss. This is just the Minimax linear regression estimator. You again have invariance with respect to orthonormal matrices. So again, the statistical game is equivalent to this reduced statistical game, where instead of working with the scale, the unit ball, I can just work with in d-dimensional space. I can just work with this one-dimensional interval. And so just as we did earlier, the maximization oracle is just a simple 1D optimization, which I can solve up to any approximation error that I want. But what about the Bayes estimation oracle? It turns out that even in this context, I can actually derive the Bayes estimator in closed form. And this is a little bit more involved, involving essentially the cumulant function of the Fisher-Bingham distribution. Again, I won't get into the details, but it's just suffice to say that it's available to us in closed form. So what I can again do is obtain the this is provably Minimax estimator, and then again test it out for different samples, different problem parameters, and we do much, much better than OLS or ridge regression. Again, the parameters for ridge regression were chosen to be the best, but even that is not going to help you, right? We do much, much better than either of those. So just one last application, which is entropy estimation. So, or a discrete alphabet. So here I'm given n samples from a discrete distribution. Essentially xi is, sorry, it should be belongs to 1 through d, right? It's xi is drawn from a finite space. And so essentially the statistical model is essentially just a simple multinomial distribution, right? And the goal here is not just to derive the entire multinomial distribution, but just the entropy, its entropy, okay? Now the domain of nature is basically the d-dimensional simplex. So this would be the statistical game, okay, that I would be interested in. Again, it has some invariances, but it's a little bit more involved, involving permutations, which I won't have time to get into. And again, we can leverage those and so on, right? So let me just skip directly to the results. So what can I do to estimate the entropy? One thing you could do is estimate the MLE, which is essentially just the empirical fraction of samples that fall into each of these bins, right? And then given that MLE, I can compute its entropy. That's what I mean by plug-in MLE. Then I can look at this rate optimal minimax estimator of Chintel Zhao and colleagues. That's the second. And this is our algorithmic estimator. And what you can see is that it is either very close or better than this famous estimator for entropy estimation. Okay, so that's basically, with just a couple of minutes to spare. So that's basically our results. What we have essentially done is this kind of seemingly crazy idea of looking at this minimax estimation as just a difficult zero-sum statistical game and just directly try to solve it, right? And again, I want to emphasize is that this is the learning to learn, right, that we actually care about, or automated statistician, or all these different phrases. This is exactly that. What we have essentially done is that we show that efficient computation of at least an approximate Nash equilibrium is possible, so long as you can solve or get access to these two oracles, which is finite dimensional maximization and Bayes estimation. Again, there are a lot of heuristics for each of these. So you can get heuristic minimax estimators, but the question is, can you get provably minimax estimators for which you need provable solutions to these oracles, which you can if you can leverage natural invariances in the statistical game. But of course, some open questions are, can we think of other constraints that are not just invariances so that the oracles are tractable? But the other thing is that instead of trying to get a very, very vanishingly small approximation error, what if I just want rate optimal, meaning that I allow for constant factor approximations? Would that allow for easy oracles? And so these are at least some of the questions. So let me just stop here and see if there are any questions.
Great. Yeah, thanks, Pradeep, for the nice talk. Any questions? Maybe I'll ask one. So yeah, I was wondering, like in this last example with the entropy, it looked like some other method was doing slightly better than yours, but I thought yours was sort of guaranteed to get the best possible risk.
Right.
So what's happening there?
Right. So we only get approximate minimax optimal optimality. So we get an approximation error, and sometimes that approximation error could be larger. Sometimes it could be small. So that's
okay. And the approximation comes from things like how many iterations you run, or like something like if you chose your parameters.
Exactly.
You could make it better.
Exactly. So if you go to the theorem, the approximation error is given here. So all of the things that he mentioned are exactly that. So the first term is the number of iterations we run. Typically, we don't run it for too many iterations. This is the first term, and then the second term are the approximations introduced by the oracles themselves. So maybe you don't solve the optimization exactly up to some tolerance and so on.
Got it. Thanks. Yeah. Okay. One more question here.
Thanks for the great talk. Regarding the first two examples, it seemed like you heavily use the rotation invariance of the Gaussian distribution.
Mm-hmm.
So will this work for non-identity or non-diagonal covariance?
That's a very good point, which I swept under the rug, right? But I guess if it's a question of what would be the invariances that it would satisfy. Again, we didn't stress test that too much, but that's basically what you need to answer. This specific invariance won't hold in that general case. You're absolutely right. In that case, what I would do is maybe just work with the reparameterized problem, right? So let's go to the problem. If I look at, I don't know, linear regression, so if I go to linear regression, then if I could maybe co-opt the covariance into theta star, right? Then so long as, I don't know, the spectral norm of the covariance is bounded, then I can push that into this and try to recover essentially the scaled parameter, if that makes sense. So I could do that, things like that. But yeah, ultimately it's a question of if these specific distributional assumptions don't hold, then what invariances would be satisfied?
Great. One more question.
Just a quick one. So this sort of was, sort of an operational interpretation of minimax risk, in that you don't actually care about R star, you're just going to get to it. Is there a sense in which, or examples of problems in which you can also, with the same type of framework, characterize R star, maybe up to a constant or something like that?
By characterize R star, so
I mean, like in the entropy estimation question, right? You can sort of, there are other results that will tell you like how R star would scale, or how the sort of minimax risk scales in terms of other dimensions in the problem or other parameters of the problem. But this doesn't care about that clearly. You're just telling me it's an additive approximation to R star. I'm just wondering if there's a sense in which you can understand the sequence itself.
Exactly. So this doesn't. So the first part, which is R star, we do get R star. You do get the value of the gain. So you can compute the value of the gain, right? Just plug in the theta hat and the theta star that you compute, and then you get the value of the gain. So you do get R star itself, but what you do not get is how it depends on various problem parameters, or maybe even you may like some simple expression. Maybe you just want the functional form of the minimax estimator. What we really get is a sample-based approximation to the least favorable prior. So what you then have to do is, given that, that's the takeaway from this, then given that you need to again derive the functional form of that prior, and then given that you need to derive the functional form of the corresponding Bayes estimator. So I haven't talked too much about that, but you could do that in some of these simple cases, like there's a lot of intuition on that for the finite Gaussian sequence model. There were various conjectures on what would be the optimal least favorable prior, and so we provide some insight into that. But yeah, in the completely general case, this is purely algorithmic. It's an interesting open question. How do you take this algorithmic outputs and extract the functional form? But that's a very, very good question. Yeah.
Thanks.
Okay, great. Any other questions? All right. If not, let's thank Pradeep again.
Thanks, everybody.
So that's it for today.